Robotik in der Industrie. Der Podcast mit Helmut Schmidt und Robert Weber. Guten Morgen, liebe Sorgen. Ihr habt natürlich keine Sorgen, denn hier ist das Robotik-Häppchen um 6 Uhr am Montagmorgen. Mein Name ist Robert Weber und wir suchen einen neuen Partner für das Robotik-Häppchen. Wenn ihr also Lust habt, Partner zu werden, dann meldet ihr euch bitte bei Helmut oder mir. Und jetzt geht's los. Guten Morgen und willkommen zum Robotik-Häppchen in der Kalenderwoche 11. Helmut und Robert sind im Vormessestress, deshalb haben wir heute ein Interview für euch zum Thema Reinforcement Learning. Verdammt wichtig für die Robotik. Geführt hat das Gespräch Robert und der Gast war Jan Kortnick. Jan war viele Jahre zusammen mit Professor Dr. Jürgen Schmidhuber, Mitgründer von Neisens und hat viele Robotic Reinforcement Learning Themen betreut. Wer erinnert sich noch an den Würfel und die Robotikhand von Festo? An dem Projekt war Jan auch beteiligt. Also Deep Dive. Und jetzt geht es los. Guten Start in die Woche.
Hello everybody and welcome to a new episode of our Industrial AI podcast. My name is Robert Weber and my guest is a well-known guest. Jan Kortnick is back. Hello Jan, welcome to the podcast.
Hello, good morning. Hello everyone.
Good morning. How are you?
I'm all right. It's a little early hour for a scientist.
It's 8 o'clock in the morning, right?
Yes.
So you define yourself still as a scientist. Why, Jan?
I'm sort of like a retired scientist, you know. And I was thinking about this because I've been listening to lots of let's say motivational podcasts in order to grow my business, and I listen to people like, you know, ex-Navy SEALs, and they they feel like they talk like, no, I don't do that anymore, you know.
But they wake up at 4 o'clock, I think.
Yes, they wake up at 4 o'clock, and they advise people just if you're going to wake up at 4, everything is going to be fine. And I don't think so.
Okay. So you are based in the south of Switzerland, near to the Italian border. So you have a more relaxed morning, right?
Yes, indeed. You know, everything is kind of a little slow. Now we are approaching the period where almost nobody will work here.
Okay.
Because a lot of religious holidays, and then everybody starts frenetically in September again. So
okay, perfect.
Kind of very relaxed here.
But we want to talk about reinforcement learning because I am seeing it come back, or am I wrong?
You're right in a sense that you are seeing it come back, but it's been here all the time, and it's been a little bit under the radar. You know, it's actually very old topic. I think it might be even older than neural networks from 40s. It's even older. It probably starts in psychology, where scientists were doing experiments with mice and little creatures, you know, and then putting them through the mazes and observing how they behave and so on.
So with DeepSeek, the discussion about reinforcement learning came up again, right? Why is it so important? What can it do that other techniques can't, especially when we talk about DeepSeek first?
Okay, so reinforcement learning, you can see it as two things. You know, when I was learning about reinforcement learning, using reinforcement learning, I learned that there are two things. We used to call it like reinforcement learning with lowercase r and lowercase l. This was sort of a definition of the problem, and then there was uppercase RL, which was the collection of the methods. And the definition of the problem statement is that you have some sort of an agent.
Mm-hmm. Oh, agent is very popular, right?
Yes, but don't get it derailed to what people call agents now, because it's something different to what we used to call them back then. But I'll get to it. And then you have environment, right? And the agent interacts with the environment. The agent can be the mouse, or it can be a human who's learning something, or it can be a robot, or it can be whatever. It can be ChatGPT. And so the agent interacts with the environment and observes the environment through observation, and then takes actions. And the actions do something for the agent's good, and then this cycle repeats. And every agent wants to maximize its future expected reward, which is the definition of reinforcement learning, you know, such that he harvests as much reward as possible. And then the reward is typically some sort of value that the environment gives him, right? And then this problem applies to many real scenarios, like driving a car, manipulating a robot hand, you know, going from A to B, learning something from the books. and reasoning, right? And now we're getting to the popular terms. Now we are getting to what are these novel models like DeepSeek doing when they actually think about stuff. So all the, let's say, I don't want to call them old language models because they're kind of like not that old, right? But these traditional ones, like the first GPT, they unroll the input sequences using that statistical model. You can imagine it as like a
database,
statistical parrot, right? Like, which has listened to lots of text, and then he kind of randomly pulls out, what fits the current input, the current problem. Whereas the reasoning models, they actually employ reinforcement learning. They employ that mechanism of interacting with the environment. And the environment here is the space of the prompts, of the texts. And they are trying to refine, comes out using the reward. And then the reward in the DeepSeek, I'm not an expert in language models, but the reward in DeepSeek was something like tested on ground truth tasks like code generation, right? And these constitute the environment for refining the model. So it's sort of the arousing moment, or the interesting part is like when you do step from feed-forward network to recurrent neural network, when you have that feedback loop and suddenly things start to become very interesting because you can work with long sequences very efficiently. Reinforcement learning brings the same to language models because it allows to refine very efficiently and get to the essence of the problem. So it reduces that, in the language models, you always have like two approaches. One is from the inside when you're trying to understand why it does what it does using, understanding how the models work. And then from the outside, from the users who actually take it and not knowing how it works, they start using it and they observe certain properties like generating random texts, right? And it has high perplexity and high randomness. And then reinforcement learning tries to bring this down very efficiently because it does, at the same time, it's very compact and creates models which are very nice. And of course, there was a lot of tricks involved.
Yeah, absolutely.
Because reinforcement learning is like, when you are grilling a meat and every minute you come with some sauce and you stick it in here and there and it makes it a million times better.
Okay.
And eventually works.
That's interesting what you mentioned, because a few weeks ago we had Professor Marius Lindauer from the University of Hanover as a guest, and he said, it's a quote, "Reinforcement learning is a beast." How do you see that? Is he right?
Well, define beast,
It's very tricky.
In a good sense.
In a good sense.
In a good sense. It's a monster tool, right?
Okay.
It's because reinforcement learning is sort of like the mother of all problems, right? Everything you do as a human, you can frame it as reinforcement learning, except some very specific problems that you're solving, right? Like absorbing knowledge through reading books, doing that supervised learning. Your father tells you how to drive a car, right? And here, there is a curb, you need to steer a little bit right. That's supervised learning.
Mm-hmm. Yeah.
But as you hop in your own car and try to get to the target and you're driving, that's reinforcement learning. Or very popular or unpopular topic, you want to get to the Mars, right? That's reinforcement learning. And the reward is, are we on the Mars yet? And that's the problem. The problem of reinforcement learning, that you have to infer all the underlying actions that lead you there. And sometimes this is very, very difficult.
Yeah, we talked about AutoML, and when it comes to reinforcement learning, he said it's a beast, and AutoML methods can help you to manage this beast, to get it in a proper way, to help the developers to use reinforcement learning. What is your opinion on that?
It's very important to distinguish between optimization and RL. So one essential property of reinforcement learning is that when agent interacts with the environment in that closed loop, it affects the environment, it changes it, which is not that apparent in the early textbook examples of reinforcement learning. When reinforcement learning was initially applied to exactly like what the mice did to the mazes, and try to navigate through a maze, which was more or less static, and you can see the whole thing, and it doesn't have many so-called hidden states, right? But modern RL is tackling the real world, you have a lot of hidden states. You don't have full observability, which is something that in the reinforcement learning science is called POMDPs, partial observable Markov decision processes. I don't want to get into this because when everybody was explaining to me how this works, you're using these terms and everything was hidden behind the fog, all the terms, which is actually a common pattern in the science now. Like if you want to make a dent in science, you invent your own terms. That's what brings you most of the popularity, like deep learning, for example, right? So there is that problem that as the agent interacts, it influences its environment, and you also see it in practice. You see it in the real life. If somebody wants to really make a dent in society, he influences or changes the rules, right? And we can see it now very clearly what's happening in the world. But the RL agent does the same thing. Like whenever he interacts with the environment, something changes. So the underlying distribution of the data changes, and he has to learn from it and navigate. And that's what makes it really hard. So that's what makes it really difficult to convert to just supervised learning problem. It's a different class of problem, and it sort of solves more essential, more difficult problem in the world than just the standard deep learning. So that's why it's so sexy, that's why it's so cool, and that's why he called it the beast.
Okay. Regardless of large language models, where do you see reinforcement learning in your project, in your industrial environment? And what is the best way to approach an reinforcement learning project? Maybe we can do it step by step. Let's go through an industrial project.
Yes. So in my experience, it's very little industries which it was very, now it had changed a little bit, but it was, it was very hard for the industrial partners to imagine that they have a reinforcement learning problem. And they approached us and said, let's say, okay, and I take AutoML as an example. They are producing something, it has some parameters, and they have to optimize them such that they make better products. And they said, oh, and we heard about this, this is sort of like the best what you can get. And they say, okay, we know all the methods in machine learning. We've heard about RL. And how can it help us? And then that's the first step when I try to convince them, okay, so you either have a reinforcement learning problem, and that's where you are making something and the path is difficult, right? Your equipment is wearing out, the environment changes when the agents could be even the workers or the robots or whatever you make, they wear out, the environment constantly changes and you have to constantly adapt to it, then you have a reinforcement learning problem. But if you have sort of like a production line which needs to be configured, like AutoML configures neural networks, for example, their hyperparameter tuning, then it's more an optimization problem. And then it's the question, how differentiable your environment is and what methods can you use. But very often it's not even there. Very often the customer sees some sort of, let's say, quality problem, right? And they are making something and they can visually observe it, and they have 1,000 people of observing LCD screens that they are making, and they look with the magnifying glass, they look for the defects. That's a story from, let's say, 30 years ago. And that's where we usually start, right? So we work with the customers and say, okay, so we have something which can be really solved quickly by computer vision. And so we can assess the quality of your products, for example. And then that's sort of like a foot in the door for us. And then the reinforcement learning or optimization problems, they come secondary, right? The customer can now assess the quality. And then they start asking questions like, what do we do to improve the quality, right? How do we turn the knobs in the factory such that we make better products, such that the quality is higher and you don't report that many defects with your system, which you have already installed? And that's the interesting part. And that's when RL kicks in. And then it has its own difficulties, right? Because you cannot really, maybe have said that in the previous podcast, so I don't want to repeat myself too much, but let's say you don't want to unleash the beast of RL directly in the factory to start turning the knobs frenetically there and to see the outcomes, right? Because you would be destroying, 100,000 glass factories per second, and that's not realistic. So what we typically do is we model the process. And that becomes our surrogate environment. And then we train reinforcement learning agents with this environment, and then we do the deployment. The deployment itself is a problem also because it has its pros and cons, and it has its tricks that you have to.
So it sounds very complicated, right?
It sounds very complicated, but it's not that complicated. You know, what is complicated for non-researchers are the RL methods, right? If you want to, let's say, make an edge in scientific RL, you have to do all the tricks with the techniques, right? Because if I go to the history, there are some methods like, you know, temporal difference and then policy gradients, which is popular where you reformulate the RL problem such that you can use the gradient to find the best paths through the environment, best state action sequences. And then there are methods like PPO, proximal policy optimization, which, you know, I'm just giving the reference to if the listeners want to look at some modern RL. PPO is one of them. And there is a lot of tricks inside, like advantage functions and how to tune the hyperparameters. Not that many. And then the derived methods were actually used in the DeepSeek. So DeepSeek uses some like group-related policy optimization, which is again derived from DPO. And if you look into the DeepSeek paper, you will see that there is a formula spanning across the whole width of the paper across multiple lines, and that's their objective function that they optimize.
Which role does data play when it comes to reinforcement learning?
If we consider deep learning simple, right, supervised learning simple, that you have training set that it can contain a lot of texts, all the text on the planet, such as in the case of language models. If we consider that simple, then reinforcement learning is harder because, as I said before, the data changes as you interact with the environment. So it's almost futile to think that you would be able to collect all the experiences, all the trajectories that the agent can walk through the environment. And that's why it's difficult, right? Because the data basically never stops generating. So data-wise, it's a harder problem. And if I refer back to what I said before, that you first want to create a model from a factory and then learn on it, creating the model is a hard data problem because you have to cover all the cases which you normally do not encounter. Because RL, it's like when babies learn, right? It's learning from your own errors. So you're walking on a path, you're working on a balance beam, and you make a sidestep and you fall, right? That's what happens in very early stages. You keep falling, and then you keep falling less and less and less. And you have to be able to cover this, right? So if you have fully software environment that you can simulate and that can even simulate the failures, that's perfect. But if you're learning the model from a factory, which is operating so because people are controlling it, you don't have these failure states. And you have a very limited amount of data in these cases, right? But you still have to explore them. So that's the difficult part of it. But it sort of removes the difficulty from the RL. It puts it more to data and puts it more to the model generation. So that's the complexity, that's the hardness in the industrial RL. Basically, lack of the models, right? That was the era of digital twins. We said that was some like 5 years ago, right? It was a big deal. Everybody was doing digital twins. And to me, it almost seemed like people do digital twins for no reason, right? But the reason is here now. And it's very important that the people have created digital twins because now we can use them in RL and optimize the agents that actually work with them as surrogates. And then we can do the transfer to the actual industry.
Mm-hmm. How do you maintain a reinforcement learning approach and practice? Or what do you need to do?
But what do you mean exactly? Like if we deploy it to a factory, what is the maintenance or how?
Yeah, exactly. What's happened then when you deployed the reinforcement learning to the shop floor or to a process in the industry sector? And what comes after? Do I need to maintain?
You fire all the employees, they go home, you pay them psychologists? No. Well, there's two things, right? You can always improve the methods. You can always tweak it. You can find something which works a little bit better, same as the deep learning, right? You can always improve it, such as it works faster, learns better, you get the better quality. So there is this kind of like a software/theoretical maintenance of it. Then there is the normal maintenance, like when you interact with the production, you get in the automation field and when you deploy something, you have to take care of it, right? Like battery runs out somewhere, computer dies and so on. These are the classic problems which were here always in automation. But, it's almost, I don't want to say like it's sort of like risk-free or nothing bad can happen because, once you deploy it, everything's well found. But as always, as in deep learning, you figure out that there are things which you haven't thought of, and then the algorithm or the RL is designed such that it would never, utilize something which is never explored, right? Like we have one customer, and then we are not doing RL there yet, but we are doing the inspection, and then he says, yeah, and then everything works, and they have the data, we label training model, it's kind of nice, and we like it, and then suddenly it doesn't work at all, and it's like, oh yes, because like once a year we engage this machine which brushes the material, and then material looks completely different, and the distribution changes, and you don't know what to do. So, but as I'm thinking about it, like maybe you have asked that you either, let's say, train a controller, which then you train it, let's say, in simulation, and then you deploy it, and then it works, and then it's fine. But maybe you ask about, like, is there an ability that the system actually adaptively improves, and that it has to be prepared for it. Same as other techniques in other fields. Like, you have to, let's say, let it allow to learn, and that's sort of not that hard, right? That's sort of like an essential property of the problem. You don't completely close to learning, right? You deploy it and you still let it observe, and you let it, collect the data and maybe run some optimization on the trajectories that you collected while working with the actual plant and not with the model. Yes, that's possible. That's kind of easy.
What are the limitations of reinforcement learning in the industrial sector?
I would say for now, it's...
No limitations.
No. But it's, as we discussed before, it's the data. Because the method is far more advanced than what the bottleneck of industrial problems allows you to do. So I wouldn't want to say that there are no limitations. It's endless. Maybe if I'm a marketing person of some kind, I would say it's limitless, but yeah, I'm still an engineer, so.
And scientist, we hear, a retired scientist.
Former scientist.
Yeah.
I rely on other scientists, and I like that very much because, we can just use what the scientists come up with and we can integrate, and I enjoy this position very much because I don't have to do all the science myself. That's hard, that reminds me our Calabrian cleaning lady at ITSIA, and when she was complaining about that our desks are too dirty and what's she gonna do, and I'm looking forward to die and go to heaven when there are no dirty desks. And I said, like, come on, what are you complaining about? It's like us complaining that there's too many open problems in science, right?
Absolutely.
Which is equally frustrating.
Yeah.
So, and now we have a lot of open problems in the intelligent automation for industry, and then we can be.
But what are the next steps when it comes to reinforcement learning?
I think there are two paths. One is the industrial, just to use it more in industry and to try to discover problems when it actually can bring the value. And then the scientific approach is just to integrate more the latest, greatest deep learning technology, like the transformer, which is being used in RL, but it's not being used very much, right? Or use modern neural networks like XLSTM for RL, which is, here and there, but it's not very popular or very massively used, right? Because a lot of people are now concentrating on language models and how to basically use RL for language model, but it's just language, right? But let's use the methods which are being used there, like to tokenize the world and not worry about the language modality, but to not even just other modalities like sound or video, that's there already, but like use the modality of movements of machines and come up with methods which can control them efficiently. Yeah, and that's sort of like a holy grail in the whole automation. It's called dark factory, right? Where you have no humans and then everything works well. And RL is one way to bootstrap these things, because essentially, it's the same problem. It's just, deployed to the field. So I would say, in theory, let's use more of the nowadays latest transformer techniques and bring it together and port it back to industry.
Finally, when it comes to reinforcement learning, which three statements can you no longer hear and why?
Agents. Now we have these agentic systems. I have a very good friend of mine who has taught me at the university about agent technology systems, and he had the agent technology group, which was like 60 people at most, I think. And the classic agent technology is about distributed AI. You have agents, which, agentic systems, how they are called, when you basically wrap a LM into some piece of code and they let interact with each other. That's fine. But again, it's an overloaded term, right? So originally it was something else. It was distributed AI and solving all the network and communication problems. And the agents were relatively simple, I would say, over there. But it was massively focused on, how to orchestrate them such that they do something good, right? Like controlling the air traffic control, where you have 100,000 planes in the air, and each of them has to communicate with each other and negotiate their paths and navigate completely without humans and completely fail-safe. That's agent technology problem, and that's what they are solving, and they were very, very good at it. And now it has shifted towards that every agent is like a very simple piece of code, and which contains that 300,000 billion weight models, and they talk to each other. And then nobody cares about the communication between them. So it has to come. So, I can really say that I hate that hearing, but it's sort of like the problems which are there are not even remotely considered, I would say. And that's my pain with that, because...
So that's the first one. The second one.
Yeah, what I didn't like was when I was at some forum and they said, okay, with these LLMs, there's that magic parameter that you tune and it does the magic, and it starts hallucinating less. It's just Boltzmann temperature for probability distribution. Like, so what I don't like is when things get like oversimplified, omitting the true nature of the problem, and it puts it in that haze, in the fog of war, where you cannot really understand what is what, rather than explaining it properly in simple terms such that everybody can understand. And what I like on that is if you do that, then people say, aha, so now it all makes sense. That, I think, is the biggest problem of the science, and I don't want to sound too bold and like feel above the people who don't really want to learn it, because the topic is just too large and you don't have enough time to study everything. So these are these oversimplifications.
Okay, that's the second. And the third one?
Depends how popular we want to get. Yeah, it's not that much of a term. It's more that explanatory problem, right? When you read a paper and then people are overusing some terms that they've invented, and it's very hard to imagine what they think, like, or what they mean with that.
That sounds a little bit like your former boss.
Which one? Like Jürgen?
Yes.
No, but he wasn't like that. I gotta defend him in here, because he wasn't the one who was inventing terms just to promote his stuff a little bit. Well, take upside down RL, for example. But he was more trying to defend it and then explain things as they are and trying to see through them. So this is definitely his good property. And yeah, but sometimes he was inventing terms. I remember once because we were doing RL, not using, let's say, the classic RL techniques, but we were using evolutionary RL, which is like a huge topic. Maybe we should do another podcast on that.
Yeah, absolutely.
It becomes very funky and it's very interesting and it's very cool because it's very simple in a sense, right? The methods are very, very simple and almost everybody can use them. Like those who cannot program, the RPO or PPO, they can definitely do evolutionary RL and do a big thing with it. We have, even with my previous company, we have even developed a library which was for evolutionary RL running on.
So can you tell it's a low code RL? What is it?
I would say it's low code RL. because you can write evolutionary algorithm as a one-liner in Mathematica, and then that.
Oh, Mathematica is coming back every
Sorry,
time we got an episode.
Yeah, I haven't used that thing last 18 years, or I know how long. But yeah, so that's sort of like a different angle to attack the reinforcement learning problem. And then we were thinking of how to call it, and we said, okay, let's call it, because we were using, as policy, we were always using a neural network, especially a recurrent neural network, especially LSTM at the time. And we said, okay, it's a deep network, which was already coined, and this is let's call it the deep reinforcement learning. And I think I don't really remember correctly, it's been 10 years ago, but I think I've had a paper, or I had like a talk at a workshop, which is called deep reinforcement learning. And when there was at NAPES, was called NAPES that time, not NeurIPS as now, but it's the same conference. They organized a deep reinforcement learning workshop, which was more about DQN, the algorithm from DeepMind, which was really well in solving Atari games. And they organized that workshop, and they actually had to invite me because I coined the term. But the term was actually coined by Jürgen, and it was when we were walking to lunch at ITSIA something like 12 years ago.
Okay, that's a nice story. What are your next projects for you and your team?
Next big thing.
Visiting Hannover Messe.
Yes, but we have a product for inspection, and we are working on a product for the actual control. And that's sort of like a holy grail. It's very difficult to do, and it's very hard to imagine that you take a box and you deploy it to the factory, and it learns there, makes a model, and trains a reinforcement learning agent such that then you can connect the box properly and it starts working. That's my sort of like a dream now. It's sort of like a holy grail. I wouldn't even call it a project at the moment, but I think we seriously consider. And it has a lot of obstacles to be solved on the way there, which constitute like 99.9% of the work before we actually get to it. But I hope we have it at some point. But it's more in the skies, like we have lots of other things which are more on the ground. That's probably what you've asked about. And these are, I'm going to Hannover Messe, that's for sure. I'm going to the AI in the Alps. Thanks.
Oh, I don't know this.
Completely unrelated event that nobody knows about.
Absolutely. It's
nobody knows what it is, right? But it's very famous. And then, opening new niches of where we can use the research to improve the industry. And here's one thing do I have time?
Yeah, sure.
So here's one thing which is, when you ask about things which I hate, maybe that's the fourth one, or maybe that's a better third one. There is a lot of areas in science and in society where we as scientists or former scientists can make a big improvement, like protein folding or like, medicine, like basically revolutionize the whole field. And it's very tempting to do so, just to take the method, which that it's very good in solving problems, enter in some field that the people don't know anything about AI, and just make a revolution there. And then you become a hero, right? But the only thing you did is just interfaced it to the new problem. And that's very tempting for this is a huge urge just to make waves somewhere where in the field that you don't know anything about, right? And you want to become a rock star. That's very, very tempting. And I'm trying to resist that, because it I don't know, it just wouldn't make me feel great that I try to convince people like you guys, you have lots of experience, and we're gonna replace you with the machines you don't know anything about, because we can do much better. That's very difficult. And also we see it in the industry when we deploy some solution to a factory where they have workers, very, very skilled ones, and now they are going outclassed by some sort of, youngsters with computers, and that comes to, again, the industrial revolution and breaking of the machines. I just don't want to cause that. AI is here not to outclass anyone. It's just here to help people to work better and be happier, maybe not work at all, but be happier. It's an important aspect. You should not make people unhappy with AI.
Jan, it was a pleasure once again. Keep fingers crossed for your next project. Looking forward to meet you in Hanover. and really looking forward to meet you at this strange event in the Alps.
It's not a strange event. It's, you have to cut it out, but what I just wanted to make it look like that we don't know anything about that because it's some sort of like a magic event that everybody would want to attend. Yeah. So
it's a magic event. Absolutely. Yeah.
Yeah. I'm looking forward as well.
Thanks a lot. Bye-bye.
Thanks. Bye.
Robotik in der Industrie. Der Podcast mit Helmut Schmidt und Robert Weber.